Hello, and welcome back to Astronomical Library, the place where we delve into the deepest mysteries of the universe. Today, we're embarking on a journey to a remote, cold, and lesser-known region on the outskirts of our solar system. This is a place that holds clues to our very origins and harbors some of the most enduring cosmic puzzles. We're going to explore the Kuiper Belt, an icy domain brimming with strange objects, home to Pluto, and possibly the hiding place of a massive, undiscovered planet. To begin, let's get our bearings. Imagine our solar system as a neighborhood. At the center is the largest house, the Sun, and surrounding it are the smaller homes of the planets. After traveling past the inner rocky planets, Mercury, Venus, Earth, Mars, and the outer gas giants, Jupiter, Saturn, Uranus, Neptune, we reach a vast, sprawling, and seemingly empty expanse. Beyond the orbit of Neptune, at roughly 30 astronomical units from the Sun, a huge region of space begins. This zone extends to about 50 astronomical units and is home to millions, if not billions, of icy objects, both large and small, that orbit the Sun. This is the Kuiper Belt. Do not confuse the Kuiper Belt with the asteroid belt, which is located between Mars and Jupiter. The asteroid belt is primarily made up of rocky and metallic objects, whereas the Kuiper Belt is a repository of icy bodies known as Kuiper Belt Objects, KBOs. Crucially, the Kuiper Belt is vastly larger and more massive. It is estimated to be 20 times wider and 20 to 200 times more massive than the asteroid belt. The name Kuiper Belt is a tribute to the Dutch astronomer Gerard Kuiper. In 1951, Kuiper theorized that a belt of icy objects existed on the solar system's fringe. He believed it was a remnant of the solar system's formation, and that, without it, there would be no comets. While his hypothesis was not entirely accurate in all its details, his vision laid the groundwork for its eventual discovery. The Kuiper Belt is far more than a cosmic junkyard. It is a massive storage locker of solar system history. The objects here have remained largely unchanged since the solar system was born 4.6 billion years ago. They are like cosmic fossils, holding clues about the primordial materials and conditions of the early solar nebula. By studying them, scientists can better understand how our planets and solar system came to be. The Kuiper Belt is far from an empty void. It is a bustling neighborhood of comets, dwarf planets, and countless icy objects, each with a unique story to tell. These inhabitants are a diverse population, ranging from tiny, pebble-sized chunks to massive bodies larger than some planets. The study of these objects, particularly their orbits, has revealed a dynamic history shaped by the gravitational influence of the outer planets, especially Neptune. The inhabitants of the Kuiper Belt can be categorized into several distinct groups. Understanding these classifications gives us a crucial glimpse into the forces that have sculpted the outer solar system. Astronomers have categorized KBOs into three main groups based on their orbital characteristics, which act as a fossil record of their past. Classical KBOs, cubanos. These objects reside in the main body of the Kuiper Belt, in a stable region between the orbital resonances of Neptune. They orbit the Sun with relatively low eccentricity, meaning their paths are nearly circular and low inclination, keeping them close to the plane of the solar system. Their orbits are stable, suggesting they have been largely undisturbed since the solar system's early days. The name Cubiwano comes from the first object discovered in this group, 157601992 QB1. These objects are like the quiet, long-standing residents of the neighborhood. Their stable nature makes them invaluable for studying the original composition of the primordial solar nebula, as they haven't been subjected to the same violent gravitational scattering as other objects. Makemake and Quaoar are prominent examples of classical KBOs. Resonant KBOs. These are objects whose orbits are in a rhythmic resonance with Neptune. This means their orbital period is a simple ratio to Neptune's. The most famous example is the 2-to-3 resonance, where a KBO completes 2 orbits around the Sun for every 3 orbits Neptune makes. This gravitational dance stabilizes their orbits, preventing them from being scattered out of the solar system. Pluto is the most famous member of this group, and these objects are often referred to as Plutinos in its honor. Other resonances, such as 1-to-2, also exist, with objects in these orbits known as twotinos. The existence and distribution of these resonant objects are a powerful piece of evidence supporting the NICE model. A theory of planetary migration in the early solar system. Scattered disk objects, SDOs. These KBOs have highly elliptical and tilted orbits that take them far above and below the main plane of the solar system. Their orbits are unstable and often cross Neptune's orbital path. SDOs are believed to have been scattered out of the main Kuiper Belt by gravitational encounters with Neptune during the giant planet's early migration. They represent the most dynamically active and extreme population of the Kuiper Belt. Eris, one of the largest dwarf planets, is a prime example of an SDO, with an orbit so eccentric that it travels from 38 astronomical units to over 97 astronomical units from the Sun. The Kuiper Belt is the undisputed kingdom of dwarf planet celestial bodies large enough to be rounded by their own gravity, yet not massive enough to have cleared their orbital neighborhood. These are the heavyweights of the belt, and they represent some of the most fascinating objects we've discovered. Pluto. The story of Pluto is central to the Kuiper Belt. Discovered in 1930, it was long considered the ninth planet. However, the discovery of numerous other large KBOs, including Eris, forced astronomers to reconsider the definition of a planet. In 2006, the International Astronomical Union (IAU) reclassified Pluto as a dwarf planet, a decision that remains a source of public debate but was a crucial step in formalizing our understanding of the solar system's structure. Pluto is not just a frozen rock. The New Horizons mission in 2015 revealed it to be a surprisingly complex world. We saw a vast heart-shaped plain of nitrogen ice named Sputnik Planitia, which is believed to be geologically active. Its surface features suggest a subsurface ocean may have existed, or even still exists, beneath its icy crust. Pluto's largest moon, Charon, is so massive, about half the size of Pluto, that the two bodies form a binary system, orbiting a shared center of gravity in space. Pluto's other four tiny moonsticks, Nix, Kerberos, and Hydra, are thought to have been formed from a massive ancient collision between Pluto and another KBO. Eris, discovered in 2005. Eris was initially thought to be larger than Pluto, which ignited the debate over planetary definitions. With a mass about 27% greater than Pluto's, Eris is a giant among KBOs. Its extremely eccentric orbit makes it a perfect example of a scattered disk object. Eris has a small moon, Dysnomia, which was instrumental in helping astronomers calculate its mass. The surface of Eris is covered in methane and nitrogen ice, similar to Pluto. But its greater distance from the Sun means its atmosphere is almost permanently frozen. Makemake and Haumea. These two are also recognized dwarf planets in the Kuiper Belt. Makemake is a classical KBO and one of the largest in its class. Its reddish-brown surface is believed to be caused by complex organic molecules called tholins, formed when solar radiation interacts with methane ice. Makemake has one small moon, informally named MK2, a discovery that helped constrain the dwarf planet's mass. Haumea is a truly bizarre object. It is one of the fastest rotating large objects in the solar system, completing a full rotation in just under 4 hours. This rapid spin has stretched it into an ellipsoid, making it look like a cosmic football. This extreme rotation is thought to be the result of a colossal impact with another object billions of years ago. The collision likely also created its two moons, Ayaka and Namaka, and a family of other icy fragments that share a similar orbit. Haumea is also notable for having a ring system, making it the only known KBO with a ring. While KBOs are stable residents, the Kuiper Belt is also the source of many short-period comets, those that take less than 200 years to orbit the Sun. These comets are essentially KBOs that have been gravitationally disturbed, likely by an encounter with Neptune or another large KBO. This perturbation sends them tumbling toward the inner solar system, where the Sun's warmth causes their icy material to vaporize, creating the magnificent tails that make them so famous. The comets we see in our night sky are, in a very real sense, visitors from the far-off Kuiper Belt, offering us a fleeting glimpse of its frigid makeup. For centuries, the Kuiper Belt was nothing more than a theoretical concept of vast, dark, and silent frontier that could only be studied from the limited vantage point of Earth. But the 21st century marked a new era of exploration, where we finally sent a robotic ambassador to peer into this frigid realm, turning theory into vivid reality. The New Horizons mission stands as a monumental achievement in this journey. Launched by NASA in 2006, the New Horizons spacecraft was an ambitious mission to perform a flyby of Pluto and its moons, and then to explore a second, smaller KBO. Its 9-year journey was a testament to human ingenuity, traversing billions of miles of empty space to reach its destination. The data it sent back didn't just add new details to our knowledge. It completely rewrote our understanding of the Kuiper Belt and its inhabitants. The Pluto flyby, 2015. The highlight of the mission was the historic flyby of Pluto in July 2015, before New Horizons. Our best images of Pluto were blurry, pixelated dots. The flyby, however, revealed a world of astonishing complexity and beauty. We discovered Sputnik Planitia, a vast heart-shaped glacier of nitrogen ice, with surface patterns suggesting it is a convection cell, where warm ice rises and cold ice sinks. This implies Pluto is geologically active, which was a monumental surprise for a body so far from the Sun. Towering mountains. The spacecraft photographed towering water ice mountains, some as high as 3,500 meters, 11,000 feet, which are believed to be floating on the more pliable nitrogen ice below. This suggests an active geological process, possibly driven by a subsurface ocean, a hazy atmosphere. New Horizons revealed a thin, hazy atmosphere surrounding Pluto, which extends far into space. This atmosphere is composed primarily of nitrogen and contains layers of haze, giving it a bluish tint. The Curran system. The mission provided our first detailed look at Pluto's largest moon, Curran. We discovered a surprising diversity of landscapes, including a deep canyon system and a mysterious reddish polar cap named Mordor Macula, which is thought to be a result of gases escaping from Pluto and being captured by Charon. The Arrokoth flyby 2019. After its Pluto encounter, New Horizons was guided toward a second smaller object in the Kuiper Belt, 486958 Arrokoth, formerly known as Ultima Thule, on January 1, 2019. It performed the most distant flyby in human history. The images of Arrokoth showed a unique contact by two spheres of icy material gently touching each other, resembling a snowman. This shape provided crucial insights into the early stages of planet formation. Arrokoth is believed to be a pristine object, a primordial building block that formed in a very low-velocity collision, and has remained largely unchanged since the birth of the solar system. It is a living fossil from the epoch of planetesimal formation. While New Horizons provided invaluable close-up data, much of our knowledge about the Kuiper Belt comes from powerful telescopes here on Earth and in space. Hubble Space Telescope. The Hubble Space Telescope has been instrumental in mapping the Kuiper Belt and searching for new objects. Hubble's higher resolution images have allowed astronomers to observe the faint light of distant KBOs, measure their sizes, and even detect their moons. The telescope's observations were crucial in the discovery of Pluto's tiny moons, and helped to characterize the orbits of many KBOs, which later fueled the Planet 9 hypothesis. Ground-based telescopes. Large, ground-based telescopes, such as the Subaru telescope and the VLT, Very Large Telescope, are used to systematically scan the sky for distant, faint objects. These surveys have identified hundreds of KBOs, including many of the largest dwarf planets. The ongoing search for Planet 9 relies heavily on these powerful telescopes, which are capable of detecting objects that are extremely dim and far away. Despite the groundbreaking discoveries of the last few decades, the Kuiper Belt remains a place of profound mystery. It's a region where our understanding is still evolving, and some of the most exciting and debated theories about the solar system are still being tested. The objects we have observed are only the tip of the iceberg, and the gravitational effects they exhibit hint at the presence of a much larger, unseen object. One of the most tantalizing and widely discussed mysteries is the possible existence of a massive, undiscovered planet lurking in the far reaches of the Kuiper Belt. The Planet 9 hypothesis was put forward to explain the strange, aligned orbits of a small group of distant KBOs. These objects, with their highly elliptical orbits, appear to be clustered in a way that is statistically unlikely to be a coincidence. Their orbits are all tilted and pointed in roughly the same direction, behaving as if they are being herded by a much larger gravitational force. The primary evidence for Planet 9 is indirect, but compelling. The gravitational influence of a planet, roughly 5 to 10 times the mass of Earth, orbiting far beyond the Kuiper Belt, is what is believed to be shaping these bizarre orbits. This hypothetical planet would have an orbit so large that it could take it thousands of years to complete. Just one trip around the Sun. The search for this elusive Planet 9 is one of the most active areas of research in modern astronomy. Scientists are using powerful telescopes, both ground-based and space-based, to scan the night sky for any sign of this gravitational puppeteer. While no direct image has yet been captured, the ongoing hunt is pushing the boundaries of astronomical observation and has already yielded new discoveries about the far outer solar system. The very structure of the Kuiper Belt, with its distinct populations of classical, resonant, and scattered disk objects, poses a complex question. How did it form in this way? The NICE model. The prevailing theory is known as the NICE model. This model suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune were not always in their current positions. In the early solar system, they were in a much more compact configuration. A period of gravitational instability caused them to migrate outwards, with Neptune moving into the region of the Kuiper Belt. This migration was a violent event, scattering a huge number of icy planetesimals, pushing some inward, others outward, and creating the dynamically hot meaning, unstable structure we see today. The distribution of KBOs we observe, particularly the resonant objects, is a powerful piece of evidence supporting this theory of a dynamic and chaotic early solar system. The mass deficit. Another major puzzle is the Kuiper Belt's mass deficit. Models of the solar system's formation predict that the Kuiper Belt should have contained tens of Earth masses of material to allow for the formation of objects the size of Pluto and Eris. However, the total mass of the Kuiper Belt today is estimated to be only a tiny fraction of that, perhaps just 0.1% of Earth's mass. This implies that the vast majority of the original material was somehow lost. The NICE model helps explain this by suggesting that a significant portion of the original Kuiper Belt population was ejected into the vast emptiness of interstellar space during Neptune's migration. Beyond the large-scale structure, the individual objects of the Kuiper Belt hold their own mysteries. Diverse compositions. We've detected methane, nitrogen, and water ice on KBOs, but their surfaces show a surprising diversity in color and composition. Some objects, like Makemake, are reddish-brown, a color believed to be caused by complex organic molecules called tholins, which are formed when solar radiation interacts with icy compounds. Other objects have a much bluer tint. This chemical diversity suggests a complex history and different formation environments within the belt. A deeper layer. Scientists are also studying the possibility of a second Kuiper Belt, or a different population of objects with much higher inclinations, forming a puffed-up torus rather than a simple flat ring. The exact outer boundary of the Kuiper Belt is also still debated, with some evidence from New Horizons suggesting a dusty environment that extends much farther out than previously thought. The Kuiper Belt is not a static, dead part of the solar system. It is a dynamic frontier, a living archive of our origins, and a testament to how much we still have to learn. The search for a hidden planet, the reconstruction of its violent past, and the chemical analysis of its frigid inhabitants are all part of an ongoing mission to understand the story of our cosmic home. The journey to the Kuiper Belt reveals a universe far more complex and dynamic than we once imagined. What was once thought to be a quiet, desolate expanse at the edge of our solar system is, in fact, a vibrant and dynamic frontier, living archive of our cosmic history. We have explored its diverse population of icy bodies, from the demoted dwarf planet Pluto to the oddball, elongated Helmia, and the snowman-shaped Erikoth, each telling a story of ancient collisions and gentle formation. The missions of exploration, particularly NASA's New Horizons, have transformed our understanding. They showed us that distant, frigid worlds are not inert wastelands, but are geologically active and rich with complex features. The images and data have provided unprecedented insights into the origins of our solar system, offering a direct look at the building blocks from which our planets were made. Yet, the Kuiper Belt holds its secrets close. The hunt for the mysterious Planet 9 continues, driven by the strange, aligned orbits of its most distant residents. The NICE model helps us understand the chaotic history that scattered its population and left it with a puzzling mass deficit. These ongoing mysteries serve as a powerful reminder that our exploration of space is far from over. The Kuiper Belt is not just a collection of rocks and ice. It is a cold, brilliant window into our past and a source of hope for future discoveries. It teaches us that the story of our solar system is one of constant change, migration, and evolution. As we continue to gaze out into the deep black, we can be sure that the secrets of the Kuiper Belt will continue to challenge our assumptions and inspire the next generation of explorers. What do you think? Do you believe we will one day find the elusive Planet 9, or is its existence just a cosmic phantom? Let me know in the comments below. If you enjoyed this cosmic journey, please give this video a thumbs up. Share it with fellow space enthusiasts, and don't forget to subscribe to Astronomical Library for more incredible stories from the universe. Hit that notification bell so you never miss an episode. Thank you for watching, and as always, keep looking up.